Welcome to Algebra 1, Semester 1, Unit 4.5, Section 7.2. I'm going to start this section by reviewing correlation and lines of best fit. How can you decide whether a correlation exists between paired numerical data? These are scatter plots, and hopefully this is review. It says, can you match the R value to a scatter plot? Use the following R values and match them to the scatter plots. We have a negative 0.6, we have a 0, and we have an 8. Okay, so I am hoping that you can see the trends here. For the most part, most of the dots are going about right here. You could draw a line through about the average amount of them, equal number above and below. And on this scatter plot, probably an equal number above and below. The line would go something like that. And on this one, you know, there doesn't seem to be a lot of correlation, but if I had to choose, I'd probably say that if we're going to give it an R value, it would pretty much go straight that way. So now, knowing what you know about slopes, I would hope you'd be able to label these just off of their signs. A zero slope is a horizontal line, so that would be your 0. Anytime a line goes up to the right, it has a positive slope, so that would be our 0.8. And anytime a slope goes up to the left, it's negative 0.6. Or it's a negative. It's not always negative 0.6, but whenever it goes up to the left, it's a negative. Okay, which linear equation approximates the best fit of the data? Well, we need to kind of fill in a line where it's through the median of these points. That's what I like to say on our lines. So the first thing I would look at, remember in math I always suggest that you eliminate the ones that don't make sense. The first thing that I would look at is the Y-intercept. We have 20, 40, 60, it's up here around 70. So the plus 40 is going to be out, the plus 100 is going to be out. We might be pretty close to 70 or 85. It's hard to say there. Now we look at the slope. The slope here is at -2. That means if you're going up on a graph, from this point, you would rise 2 and run 1 to the left. So a pretty steep slope. In this graph, it's 0.25. I would suggest switching that back to a fraction, which is -1/4. Remember, you can put it over 100 and then reduce it because it's in decimal form. So from this point, you would rise 1 and run 4. Now you know that it appears to be closest with the Y-intercept to this one. Does the slope appear to be close to this one or closer to that one? I would hope that you said this one. Okay? Can you describe the correlations of the scatter plots? This one goes up to the left, so it's negative. This one goes up to the right, so it's positive. And this one has no correlation. If you look, there isn't a trend at all in that whole thing. You have some high and some low and some low and some high. And unlike this one where it was a 0 trend, this one is all over the place. There's no correlation. Using the scatter plot shown, what would you expect the temperature in Nevada to be at 2,500 meters elevation? Well, it's always important to read your graph axis and your title. This is Nevada. This is your elevation. So they're wondering at 2,500. That would be right here. And they're wanting to know what the temperature should be. Well, I would just draw a trend line in there say, I would guess that that temperature is somewhere between 0 and 5 degrees Celsius. Okay, that gives us a rough window that we could say that it could be, because your trend lines might not be the same as mine. At around what elevation would you expect the temperature to be 15 degrees Celsius? Well, this time we go to our Celsius temperature, go to 15, come over to about where our trend line is, and drop down. I have between 500 and 1,000 feet. Because down on this axis is our elevation. Whoops, not feet. I am so sorry. Meters. That's why it's important to read our axis. Okay? So, you shouldn't copy mine. You shouldn't have windows on yours. You should just tell me what your trend line comes out with. If it doesn't come out within my window, then ask questions at the beginning of class. How do you use substitution to solve a system of linear equations? You're going to answer that question when you come to class. So when you get done with the notes here in just a minute, go ahead and answer it so you have it ready. Here's how substitution looks. What we do is we take the value for the variable in one equation and plug it into the other equation for that variable. So here we say x equals 2. We're going to plug that 2 in for the x value in the other equation. Y equals 2 times 2 plus 4. Y equals 4 plus 4. Y equals 8. So we know that the solution to this equation is 2, 8. You do have to write it as a point because I need to know that you're remembering that it is a point that you're solving for. Now this one is a little more like what you'll see most of your problems to be like. I have that y equals x plus 3. I plug that x plus 3 in for y. So I now have 2 times x plus 3 plus 4x equals 12. Eliminate the parentheses. I have 2x plus 6 plus 4x equals 12. Now I combine my x values. 2x plus 4x is 6x plus 6 equals 12. 6x equals, I subtract 6 from each side, so I get 6. Now I divide each side by 6, and I get x equals 1. Now remember, you're not done with the problem. You've only found the x value of your point where they cross. So we have x equals 1, but now we need to plug in to get our y value. Y equals x plus 3, so y would equal 1 plus 3, which means 4. So there's our solution to the system. Okay? Why was substitution method convenient on those? Well, it was probably the most convenient because we had one variable isolated in one of the equations. So, in other words, in this equation here, we have x equals 2. That's how come substitution was so easy. And in this one, we had y equals x plus 3. That's what made substitution so easy. We could just plug the value in. Thank you very much. We'll see you in class tomorrow.